Thank you, Bob, who's coming, and Jennifer, I loved your questions. Yeah. I loved those questions. But we want to allow some time for members of the audience to ask their own questions.
I have a question. It's a mechanical question.
I think people want to hear your question, so you're going to have to use the microphone.
Okay, my question is a simple mechanical question for Jennifer, and that is, what will be the end of our solar system? How will that play out?
Well, it depends on it depends on your theology of whether you believe in the Lord's return, this kind of thing. The mechanical question is that we have a star. Our star is a G star, class star, which will progress into becoming a red giant at some point, and will expand in that process, which means the planets, especially those in the inner part of the solar system, would heat up to an uncomfortable degree. And we are in that path, which means in a few billion years, we need to move elsewhere. But we've got some time to think about it. Okay?
You used the term 13.8 billion years as the start of the universe. Where did that come from?
Oh, good question. So how do we know how old the universe is? It's really interesting because there's several independent indicators that are telling us the age of the universe so that we can even get it to a decimal place of accuracy. One is a kind of simple-minded rewinding, this whole expansion of the universe that we've heard about earlier today. You can kind of turn that around. You can tell how fast galaxies are seeming to move apart from each other. They're actually being carried along with the stretching of space, which is what's actually happening. But if you kind of rewind that a little bit, you can kind of come up with a rough approximate age. Now, it turns out that expansion has not been happening at exactly the same rate throughout the history of the universe. So that gives you a first call. You can then test the actual rate of that expansion by looking at very distant galaxies and seeing how fast they appear to be radially separating from us and compare that to those nearby us. And remember, you're looking back in time, so that way you can gauge the expansion rate of the universe far back in history and gauge it all the way up to now, and so you can get a more accurate view of the expansion history and how long that's been going on. But then we also have something called the cosmic microwave background radiation. So the idea is that if the universe did begin with a sort of big bang, an energetic burst, there would be leftover background radiation filling the entire universe. So the idea of the Big Bang is not that there was a little explosion within a huge universe, but that the whole universe was spatially contracted from what it is today, and that the Big Bang happened everywhere at the same time. It's just that everywhere was more compact, and that everywhere has been expanding. So you have leftover radiation filling space, but as space expands, the energy or the temperature of that radiation drops. And so the prediction is, if this theory is true, you could find this background radiation in every direction of the sky. And as was mentioned in the talk before mine, Bob mentioned that this was actually detected, and the Nobel Prize won for it, for this cosmic microwave background radiation. You can measure that very carefully and discern the age of the universe that way, and it also corroborates with something about 13.8 billion years. So you can also look at the age of individual stars, and the oldest stars that we know of, again, stars don't last forever, but if you can find stars that have been some of the earliest stars in the universe, you can gauge their age, and it also it complements these other studies. So there's several different directions, and they all point to this particular age.
The question for Dr. Russell. I was hoping you might have some time to talk about NIOTA. I know it's a very complicated subject, quantum mechanics and how it interfaces with theodicy, but is there anything that you could say on that subject here, even if briefly?
Well, thanks for the question. I'll be very, very brief because of time. The question is, can we think of God acting in nature to make a change in nature, to guide evolution, if you like, in a way in which God's action doesn't violate the laws of nature or violate the processes of nature? And the answer is yes, you can, because of quantum mechanics. So I call it non-interventionist objective divine action. It delivers on theism without ID.
Yes, thank you. I hate to have myself be another questioner, but I'm doing that. I'm fascinated by this entire symposium, and again, I thank all the participants and everybody who came. My question is, I know you mentioned nuclear fusion in your comments. We are facing a huge drought in this country and in this world in different sections. Do you have awareness of nuclear fusion technology in being able to move our water from one region of the world to another to solve the problem here in California?
I assume you're addressing that question to Professor Russell.
No.
Well, I can't answer that question, but I think you asked a question that's in a broader realm, a very good question. How do we harness some of these interesting things we're finding in basic research and use it to solve very real practical problems? And of course, many people are trying to do just that. So you ask a good question. I just don't know the answer. I mean, the whole business is a different problem, but the whole issue of energy, you've got solar power. The sun is just churning out energy like crazy. If we could just figure out how to harness just a little bit more of that, it would be, fantastic. So things are available, resources are available, clean resources. We just need to figure out better how to utilize them. That's a real calling, actually. I think it's a godly calling.
We can take one more question. And we always privilege the students for the final question. Oh, come on.
Professor Russell, you said that one of the many ways in which the world could be possibly created, one of the possibilities, you said that the world would, or the universe would collapse and thereby regenerate itself. So how could a t = 0 possibly exist in a self-generating sphere?
I'm sorry, can you say it again a little louder? It's hard down here to hear it.
Oh, sorry.
Sorry.
If you have, you discussed in one of your possibilities of how the universe can be created, that the stage 3 was a never-ending cycle, that the universe would die in order to reborn itself. But in a possibility like that, how could t ever equal 0?
Okay, so if I understand right, in a cyclical universe, a universe that recreates itself, how could there be a t = 0? You're right, there isn't. It's one of the ways in early cosmology people got around t = 0 by saying, well, the universe didn't come from a big bang, it bounced from a previous universe. And one reason why it could be true is because of quantum mechanics. Because after all, the universe obeys quantum mechanics, meaning if it's small enough, like an atom, that it obeys quantum mechanics, it could not collapse further, just as atoms can't collapse. So there were sort of heuristic reasons for thinking t = 0 was not correct. It actually must have contracted and bounced and become our universe. Okay? Thank you.
Thank you very much.
The inspiration of this symposium was largely the historic Romana's manuscript that Santa Clara now has. And while the symposium here will formally end, that exhibit is open. So we want to invite you to proceed to the reading room of the archives and special collections on the 3rd floor of the library and Learning Commons to view it, as well as other historic manuscripts related to science and religion. The exhibit hall adjoining the reading room on the 3rd floor will be open to symposium participants to sneak peek a forthcoming exhibit entitled The Philosopher's Cabinet, 19th Century Science at Santa Clara University, and that will be available on viewing until 5 o'clock. For those of you in Professor Putz's class, thank you for your patience with my teasing of you. But please meet right outside of the Music and Dance building to walk over with Professor Putz and view the exhibit together. We're very grateful for any evaluation surveys that you have. It helps us in our own planning. We greatly appreciate your feedback. And most of all, we are grateful for a very, very fascinating 24 hours, both to you as well as our panelists.